Picking up where we left in the last video, we'll now look at type 1a supernova. So type 1a is a very different cause of the supernova, and it sort of makes sense if you look at type 2 to identify how they've formed because of a large star that has used up all of its fuel. Type 1a supernovae result from actually a binary star, and one of the stars in this binary pair is a white dwarf. So white dwarf being the long dead remnants of another star. They're fairly dense, and so their gravitational pull is quite large. So as a result, the steps that we're interested in here is the fact that the white dwarf, I should mention too, the other star could be any other type of star really, could be a main sequence star, red giant, or even another white dwarf. So the white dwarf is going to accrete. That word accrete, we're basically sort of saying it steals the mass. So it accretes mass from its binary partner. So some of the mass from the other star is dragged into the white dwarf, and as I said earlier, that's due to the white dwarf's strong gravitational pull, and that strong gravitational pull is basically a result of the high density of the white dwarf. So there's the first step. It's going to pull some of that mass into it from the other star, and ultimately that means that the white dwarf is going to get bigger. Now, if you cast your mind back, we talked about a limit to the size of white dwarfs. So when the white dwarf reaches the Chandrasekhar limit, and if you recall, the Chandrasekhar limit is 1.4 solar masses. So when the white dwarf gets to a size of 1.4 times the mass of the Sun, it's going to collapse under its own gravity. Now, if you think about this situation, the white dwarf is not there's no fusion that's going on here, so there's not a whole lot of radiation pressure. So the large gravity is going to start to cause the white dwarf to collapse in on itself, and as it collapses in on itself, that's when we're going to see some more fusion occur. And the fusion that we're dealing with here is of carbon and oxygen, and as a result of that fusion, it generates enough radiation, or enough radiation pressure, I should say, to blow the star apart. So it blows the white dwarf apart in a supernova. So that's the type 1a. Fairly straightforward, just basically the white dwarf gets too big, having dragged some more mass into itself, and eventually gets too big, and just sort of the radiation pressure that's caused from the fusion of carbon and oxygen is just too much, and the star can't cope, blows it apart. Now, type 1a particularly useful because we know that they're always going to undergo supernova at the Chandrasekhar limit. That means that we know how bright they actually are. And if we have something out there in space that we know what the brightness is, that's a very useful property to know, and so we can use them as standard candles. So what we mean by that is that if we know the brightness, then we can start to compare them, and we can start to use the fact that we can see these type 1a supernova occurring, and that therefore we can start to make some measurements based on the apparent brightness. So by measuring their apparent brightness as seen from Earth, we can then figure out how far away they are. So very useful phenomena to be observing. So we can then calculate distances to the galaxies that they're in. And we're really sort of talking up to about 1000 megaparsecs. So calculate the distance to the galaxy it was in, and like I say, up to about 1000 megaparsecs away. So one of the particularly useful aspects there is this standard candle idea. Type 2 supernova, we can't do that same sort of thing with. We don't know how big they are, but type 1, because they're always going to be occurring at that Chandrasekhar limit, we can then use the type 1a as standard candles. Now, a couple of differences between type 1a and type 2, so some other reasons that we can tell these two apart. The first thing that I did allude to earlier, but I want to just make it a bit clearer. Type 1a are usually from old long dead stars, and old low mass stars, to be even more precise. So they're low mass because the star then sort of didn't have enough mass to undergo a supernova in type 2, so as a result it formed a white dwarf instead, and so we can identify that type 1a are formed from low mass stars, and we also know that they have no hydrogen lines in their emission spectrum, and we know that because they are white dwarfs, or caused from white dwarfs, so no hydrogen lines in the emission spectra, and that's because all of the hydrogen fuel has already been used up. And so for type 1a we don't see any hydrogen lines in the emission spectrum, and that's, as I said, since white dwarfs have already used up all of their hydrogen. So there's the first couple of points that are important about type 1a. Now, comparing that to type 2, type 2 are usually from younger, more massive stars. As we talked about in a previous video, the lifetime of the star is largely determined by how much mass it has, and so a younger star is going to tend to be more massive. And we know that type 2 have to occur from fairly large stars, so 8 solar masses or greater. And so they're going to be young as a result. And the other thing here as well is that they do have hydrogen lines. So if you're observing an emission spectrum, the first thing that you'd really have emission spectrum of a supernova, the first thing you'd probably look for is to see if there is hydrogen lines, and if there is, then we can identify that it's going to be a type 2. If there aren't, it's going to be a type 1a. And the reason why we do get those hydrogen lines is that hydrogen is still fusing in the outer shell of a type 2. So there's two key differences. In terms of the light that's emitted, type 1a tend to be a fair bit brighter, or an order of 10 times brighter. So they emit light up to 10 to the power of 10 times the luminosity of the sun. And the way that occurs is that basically we get occurs fairly quickly, so rapidly reaches a maximum or a maximum intensity, and then decreasing over about sort of a 6-month period. So it's not that it appears and then disappears really quickly. It appears and then over the next 6 months will decrease and eventually disappear after that sort of time period. Type 2 aren't quite as bright. Like I said, sort of about a factor of 10 smaller. So it's still bright events in the galaxies that they're in. So they do tend to outshine other stars in their galaxies. They emit up to 10 to the 9 times the sun's luminosity. And there's also a bit of a difference in the way that that the light fades over time. It usually falls from a maximum, and there's a little bit of a plateau. So for a few days the intensity will sort of even off or sort of flatten out for a bit. For a few days, and then will decrease after that. And it will tend to decrease a bit more rapidly. So there's some of the comparisons then between type 1a and type 2. Like I said, they're the only two that we need to deal with, but you do need to make sure that you can distinguish between and that you can explain the differences in terms of how they're formed. So type 2 being sort of the use of the larger and larger fuel sources until iron is formed, and then the implosion that results in the large explosion. And then type 1a being the white dwarf that gets a bit too big, reaches the Chandrasekhar limit, collapses in on itself, and undergoes a supernova.